So, I'm Rodrigo, I'm a postdoc at the group, and I'm presenting today part of my PhD thesis. During my PhD, I have trying to understand how to deconstruct the cell wall. So the molecular aspects of the constructions of the cell wall for biofuel production especially. So it's basically, we want to understand basic aspects of the whole process of biomass conversion. And today I'm going to talk about the nanoarchitecture of cell walls. And the motivation for that is that the construction of the cell wall is very dependent on how the cell wall is assembled in the plant. So we can actually use the components of the cell wall for not only biofuels, but also lots of different aggregated valued compounds. Like actually, we can make building blocks for a lot of different things. So here we have some a scheme, so you can see how different things can be built in a sustainable way from cellulose, hemicellulose, and lignin, which are the components of the cell wall. So, but to do all of these processes are not really easy to do because we have what we call cell wall recalcitrance. Cell wall recalcitrance is actually natural resistance of the cell wall to be deconstructed. So what we're doing is try to understand the nanoarchitecture of the cell wall so that we can understand what keeps the cell wall so strong to be deconstructed. So it's more from a basic science point of view. So the cell wall is composed by cellulose, hemicellulose, and lignin. So you have two kinds of carbohydrates. Basically, you have cellulose, which are assembled in a crystalline structure, which is the most important part of the cell wall, and it creates the backbone of the cell wall. And we have hemicellulose, which are amorphous polysaccharides that absorbs on the cellulose, and have lignin that can protect the cell wall against external factors. And these polymers assemble in this hypothetical structure. This is this architecture that actually it prevents the enzyme from attack the cellulose, which are cellulose molecules, which are what we are interested in convert to products. So in order to deconstruct this structure, we have usually to perform some kind of pre-treatments, physicochemical pre-treatments that can disrupt the structure. And for example, here we have some cellulose, and we have hemicellulose in green absorbed on the cellulose, and have the barrier of lignin. So we have some physicochemical pre-treatments that can disrupt the structure and expose the cellulose, hemicellulose, and lignin to enzymatic attack. So one of the changes that happen when we submit this cell wall to pre-treatments are the solubilization of the hemicellulose, the carbohydrate that remains absorbed on the cell wall, on the cellulose, and it solubilizes the cellulose. So we have the polymer becomes lots of monomers and oligomers, right? And the lignin barrier also are removed or are translocated to other part of the cell walls, so that the cellulose becomes exposed to enzymatic attack. So, and this interesting thing is that all of these processes are driven by the solvent. So the pre-treatments are based on solvents in different conditions, right? So what we want to understand is how, one of the questions is how different solvents or different thermodynamic conditions can affect the cell wall structure or nanoarchitecture. And for that, we use a kind of computational model. It's not based on molecular dynamics, but it's similar to molecular dynamics. In molecular dynamics, you usually have a structure, and you know how the molecules interact with each other, and you solve the equation of motions, right? And from the trajectory, we can compute thermodynamic properties, right? But sometimes you have to run a long time in order to get convergence. In some cases, this is not very easy, right? It can take a very long time. There are other methodologies. It's not simulations, but it's based on statistical mechanical theory. That instead of running simulation to get a trajectory and then computing averages, we actually use statistical mechanics to compute the average properties from the ensemble averages, right? So I'm gonna present just the idea of this methodology so you can have a feeling of how it works. It's based on the radial distribution function formulas of statistical mechanics. And the radial distribution function is just how, for example, if you have a monatomic fluid and you pick up one of these atoms and this blue one, and then you look around for a given distance and you count how many atoms there are from a given distance from these atoms. And then you do that for a range of distance, and then you have how the structure of the liquid varies according to the distance. And the good thing is that the statistical, once we know the distribution function, we can compute any thermodynamic properties we want from the statistical mechanics. For example, if we know the G of R distribution function, we can express the internal energy in terms of an integral of the distribution function. We can compute the pressure, we can compute the chemical potential, and from this you can use thermodynamic relations to compute anything you want. Right. But the question is how we can obtain the distribution function. There are a lot of different theories, right? And they're collectively known as integral equation theory. Basically, we have an integral equation for the distribution function, right? And if you know how to solve these equations, we can use analytical expressions to compute the thermodynamics. This is what we do with this theory. But this is very simple. This is a very simple case. This is just for monatomic fluid, right? We want to apply a similar approach to cell walls. And so there's another, this is actually a generalization of in the previous slides. So it works on a more complex system. So when you have a solid, like cellulose, for example, immersed in a given solvent, for example, water, right? So this theory, if you know the coordinates and you know how these molecules interact, we can solve a set of integral equations that will give the local density of the solvent around this solid, right? So instead of having just some monatomic fluid, a homogeneous fluid, we have a solvent, a solute immersed in the solvent, and you have the correlations between the solute and the solvent. So we have the local densities of the solvent around the solute. So this is the integral equations. So I'm not going into detail, but once we know the correlation functions, how the distribution function, there are a lot of analytical expressions that can be used to compute the solvation thermodynamics. For example, here have the chemical potential or solvation free energy as a function of the correlation function, right? This is a function of the integration function. It's an integral around over all the space. So I'm gonna first illustrate how I can use this theory to analyze the hydration structure of water around the cellulose. So cellulose is composed of glucose, and the glucose it's composed of chains of glucose, and these chains pack together to form fibers like this. It's 36 fibers. They pack together in a crystalline way and form these fibers. So here we have a hydrophobic phase. It's more, although it's not hydrophobic, it's more, you have less hydrophilic groups than these other phases, right? So we have essentially two kinds of phases in this kind of fibers. So then we immersed this fibro in a bath of solvent, and then we compute the solution structure around this fiber. So here you have the three-dimensional distribution of water around the cellulose. So this is the kind of data that we get from the theory. So you can see that it's quite heterogeneous. So because the cellulose surface has lots of different chemical groups exposed, so we have different specificities. So water distributes not homogeneously over the surface. So we can also look at the one-dimensional profile of density above a given surface. For example, this picture, right? So I can take this 3D distribution and just average out the, like take the average over the plane, and then express the distribution function just around Z, for example. So here you have a scheme, as you can see here. And this is interesting because it shows that the different cellulose surfaces induce different ordering of water because the surfaces are different. For example, the hydrophilic surface is more water-like because the hydrophilic surface has lots of hydroxyl groups exposed. So the change of the water structure close to the hydrophilic surface is less intense than over the hydrophobic surface, because the hydrophobic surface is very different from it doesn't have hydrogen bonds, for example, so the water organizes a lot more over the hydrophobic surface. And you can also look at the maximum density of the water over the cellulose surface. For example, this curve suggests the peak, the first peak of the graph, like that, and it shows the density, the maximum density in different range, in different temperatures, different densities. So you can see that this is susceptibility of the hydrophobic surface with changes in solvent density and temperatures very higher than the hydrophilic surface. So, and this is conditions that happen in pre-treatment. For example, hot water pre-treatment and steam explosion pre-treatment. So this graph shows that most of the changes induced by the solvents in pre-treatment will occur in the hydrophobic surface, not hydrophilic surface. But in the cell wall, the cellulose is not just one fiber. There are a lot of different fibers, and these fibers interact with each other. So what we want to do here is to compute how one fiber will interact with each other. It depends on the solvent, right? Because if you have a solvent layer in between two fibers, this solvent layer will affect the effective interactions between these two fibers. So what we, instead of just computing the density, the hydration structure around a given cellulose fiber, we can take just two cellulose fibers, for example, this scheme, and you can move them apart and compute or solve the three-dimensional equations for every separation and get the structure, and from that get the thermodynamics as a function of the distance of the cellulose. So here we have the solvation structure as a function of the separation. So you can see here that this model of cellulose we have when they are packed together, the waters are just around, and then as they move apart, water starts entering in between, and then they create a whole solvation shell when there are not space for water in between the cellulose surfaces. And from that, we can obtain the whole thermodynamics as a function of this arrangement. So this is what we get from that picture before. So this is the free energy profile. It shows how the free energy changes as we disrupt a cellulose contact. And we have this in two different temperatures. It's kind of a simulation of a pre-treatment, hot water pre-treatment. So what we have here, for example, 300 kelvins, we have a first minima, and we have a large barrier, and we have a second minima, and this is for hydrophobic contact. For the hydrophilic contact, we have something similar. And then when we increase the temperature, the first minimum gets very more stabilized. So this is a thermodynamic force that induces aggregation of the cellulose cellulose fibers. So, and this is also what we observe experimentally. So X-ray diffraction, for example, shows that the crystallinity of cellulose increases as you increase the temperature. So it means that different fibers are packing together and increasing the degree of crystallinity of the solvent. And you can also, from this free energy profile, we can obtain, for example, the free energy of aggregation in a lot of different conditions. And this is what I show here in, for example, in a range of temperature, in a range of density that covers different pre-treatment conditions. And you can see here that, again, the hydrophobic arrangement is much more sensitive to changes in the thermodynamic conditions. And the hydrophobic arrangement can also change qualitatively. For example, in 300 kelvins, the free energy of aggregation goes above 0, which means that cellulose doesn't aggregate through the hydrophobic surface in room conditions, but it can aggregate in room conditions through the hydrophilic surface. But when you increase the temperature, everything aggregates, even the hydrophobic surface, hydrophobic contact. And another aspect of these treatments is that when you increase the temperature, the hemicellulose solubilizes. So now we have a situation where you have different cellulose fibers, and also we have water, and you have now sugars, like monomers of hemicellulose. So what does, so the question is what is the effect of having monomers around the cellulose in the effective cellulose aggregation? It turns out that as you increase the hemicellulose concentration, the minima of the free energy of cellulose aggregation gets deeper and deeper and deeper, which means that hemicellulose monomers can stabilize the cellulose contact. But what happens here is that if the cellulose fibers are aggregating, that means that water is not solvating the cellulose very effectively, right? So the cellulose interactions are stronger than the solvation capacity of water. So otherwise, the cellulose would be apart from each other. And what happens here is that when you add monomers in the solution, water, instead of solvating the cellulose, will interact with the monomers of hemicellulose. And then the water will be less available to solvate the cellulose, and then the cellulose aggregate to each other. So as increase the concentration, we have this behavior. And the more interesting is that different hemicellulose will induce different degrees of aggregation, as this free energy of aggregation shows as a function of the concentration for different hemicellulose types, right? So that means that the hemicellulose composition of the cell wall will affect the result of the pretreatment of the biomass. And from this theory, we can also, instead of analyzing the EMFs, so free energy profile, we can compute forces. And this is not mechanical forces only. For example, let's imagine we have two cellulose fibers, and these cellulose fibers will interact through electrostatic interaction. So you have an electrostatic component, you have van der Waals component, and you have another component that's not mechanical. This is thermodynamic. This is a solvent effect, which comes from hydration. So if you don't have water and you approach two cellulose fibers, they will interact with electrostatic and van der Waals forces only, and they will aggregate. But when you have the solvent might prevent this aggregation, will make it more difficult. So this hydration force comes from it's computed from the solvation free energy, right? Which means basically that we measure the force between two cellulose fibers and you average out all of the degrees of freedom of the solvents around the cellulose and in between. And everything is accounted for this term of the mean force, the effect force between two cellulose fibers. And here you have different components of the interactions, and the mean force, which is, for example, we fix to a given distance of the cellulose, and we measure the effective force between these two cellulose fibers, and which is the black curve. So we have the minimum, have the maximum, and we have a kind of repulsive force. That is the force required to expel solvent molecules and the cellulose approach each other. And we see that this repulsive force comes just from the hydration force, which is the component of expel water molecules from the interface. And the cellulose force, that's just mechanical force, is always attractive. So what keeps the cellulose apart from each other, in some cases, just the hydration force. This is just a solvent effect. And more interesting is that when you plot the hydration force in a log scale, we see that in short distances, the hydration force it oscillates a lot, right? And increase as we decrease the distance, the hydration force increases exponentially, but it oscillates with the period of the size of a molecule of water. So what's happening here is that when we bring two cellulose fibers together, the hydration structure, the hydrogen bonding structure, must be disrupted as they approach each other. And the water structure between the two cellulose fibers are also periodic, right? So they have. That's why we have this oscillating behavior. And this force, the closer the cellulose fibers, the stronger the hydration structure in between, and then the stronger the force necessary to expel this water molecule to the bulk, so that the cellulose can aggregate. This is actually a universal behavior. It happens with all the surfaces and can be measured experimentally by, for example, surface force apparatus or AFM, things like that, on the first microscope. This is this pattern is, it happens in other situations. And to finalize, I will present some study of all the parts of the soil. So I was looking at the cellulose and how it interacts with each other. And now I'm looking at the matrix of hemicellulose and lignin that pose the cellulose fibers. So just to talk about lignin, lignin is not a carbohydrate. It's a polyphenolic material. It's very complex. This is a three-dimensional network of polyphenolics. But lignin is made of basically 3 different units. The H, G, and S lignin, which differ from each other by these methoxy groups attached to the aromatic rings. So the question is how lignin, lignin monomers interact with the hemicellulose, and what is the effect of these methoxy groups in these interactions. So for that, I perform also 3D resin calculations. So I have, as a solid, I have a hemicellulose chain. So I have in the middle of the solution hemicellulose chain, and I have now a solvent composed of lignin monomers and water, but lignin monomers in increasing concentration. So I see the response of the system as I add the lignin monomers in the solution. So this is the thermodynamics, right? So as I increase the lignin concentration, I observe a decrease in solvation free energy, which means that the lignin monomers are comfortable around the hemicellulose. The more lignin I add there, the more stable is the system. Which means that lignin and hemicellulose have affinity to each other. And also I see that different lignin interact with different intensities with the hemicellulose. The S lignin, which bears more methoxy groups, interacts stronger with the hemicellulose than the H lignin that has no methoxy groups attached to the aromatic ring. Okay, so now we have here the distribution of water and lignin around the hemicellulose. So here you can see what is the nature of the interaction. So in orange here we have the hemicellulose chain, and we see that the water coordinates especially the hydrogen bonding sites of the hemicellulose. So water doesn't interact with the hydrophobic site faces of the hemicellulose. On the other hand, the S lignin, which I'm showing here, covers especially the hydrophobic faces of the hemicellulose. So what is happening here is that when you have just water interacts with the hydrogen bonding sites, the hydroxyls, but also water interacts with the hydrophobic faces of the hemicellulose. When you add lignin starts interacting with the hydrophobic face of the cellulose and expel water to interact stronger with the hydrophilic part of the hemicellulose. So the picture you have here is that when you have both together, water will interact with what water likes, and lignin will interact with what lignin likes, and water will not interact with what water doesn't like. So that's why we have this thermodynamic behavior, and it also explains why the methoxy groups attached to the aromatic ring stabilize more than the H lignin, because as we have these methoxy groups here, we have actually a larger surface area of these monomers. So the surface area can cover more effectively the hydrophobic phase of cellulose and prevent water from reaching the forbidden regions of the hemisoils. That's why we have this profile here. So this is also, to have this experiment sometimes, so some genetic modification that increase the S lignin and reduce the H lignin or G lignin actually results in more stronger cell walls, so they need more intense pre-treatments to strengthen the cell wall. And the opposite is true in some cases too. So that's why. Questions?
Near the beginning of the talk, when you were looking at this radial or kind of orthogonal distance or density functions for water and the hydrophobic and hydrophilic surfaces, yeah. I mean, the hydrophilic surface, it's really, I'm just wondering why you're looking at the maximum instead of, for example, the integral or something. Is the maximum, I mean, to me, you learn a lot by taking the integral of that first peak in the hydrophilic surface.
You mean the coordination number?
Yeah, something like I don't know if it's exactly a coordination number in this case, but the fact that the hydrophobic peak is higher doesn't necessarily tell you, it's somewhat misleading, right? Because you expect more water near the hydrophilic surface.
Yeah, I agree. But in this case, the integral would, the peak would, for example, if I integrate until this point, as how do I say the laguna? The width are pretty much the same, I think.
So the width, that was, I guess, a follow-up question. When you increase temperature, is the shape staying the same?
Yeah, it keeps. Yeah, it doesn't change a lot. Yeah, actually I have this data, but it doesn't change a lot. That's why I just showed it.
May I add one comment? Yeah. From that plot alone, we can just tell that perhaps in the around the hydrophobic surfaces, water is perhaps more organized, quote unquote, than around the hydrophilic surfaces. Because you have a sharper peak, you have a taller peak, so it means that the degree of correlation between water molecules. But that is that is water correlations, right?
Sure. Yeah. Just one comment. This distribution function is not normalized with respect with the ideal gas.
Sure.
It's normalized with respect to the bulk, right? So this means that water is more organized on the hydrophobic surface, which means that the hydrophobic surface disrupts much more the bulk structure of water than the hydrophilic surface, right? Because the hydrophilic surface can provide a lot of hydrogen bondings, so the tetrahedral structure of water are less disrupted in the hydrophilic surface than the hydrophobic surface.
Yeah. That's what I say, quote unquote, organized structure. Because what is organizing the structure and what is disorganizing the structure? Those are very loose terms that we don't know how to quantify. The only thing that we can tell, that's for sure, because geovars measure correlations between particles, is that water around the hydrophobic surface tends to be more highly correlated with each other, because near a hydrophobic surface we don't have, or they don't have hydrophilic stuff to bind to, so they bind to themselves. So that's why the peaks are sharper, so the waters are more correlated with each other. Now when they are near a hydrophilic surface, then besides other molecules, they have the surface to bind to. So they have some sort of competitors. That's why you have a shoulder to the left on the red curve, and the shoulder has some wiggles, and these wiggles probably is due to you have one step ladder type of situation. So that's I just want to add in this comment that
Yeah.
It's more organized or it's less organized, structural promoter, structural deconstructor.
Yeah, I'm
These
just
are dangerous
thinking
terms.
about because in pure water you have the hydrogen network going, and over the hydrophobic surface you don't have this anymore because you don't have hydrogen going inside the position to keep the structure.
Have you actually characterized the structure and dynamics of this water using tetrahedral order parameter or orientational correlation functions?
I can't. Yeah, I can't do that with this theory. This is just
Sure, but I mean, now you could do an atomistic simulation.
Yeah, I could do that with
Okay.
energy.
Could be really interesting and compare it to a generic
But
hydrophobic interface.
it hasn't
and
done.
hydrophobic interface.
Yeah, for sure, it has to be done.
What is the typical bundle size?
Typical.
The size of the fiber.
This fiber,
The real one and yours.
mine is 16 glucose, and the real one is over 1,000. But I don't think it matters here. I don't think it because this is periodic. So for this kind of things, it doesn't matter the size. Because if I analyze here, for example, this property, this dx, the y was performed in the bulk of the cellulose, right? So the boundaries of cellulose doesn't enter in the calculation.
Well, if you consider the case of melanin, in terms of biopolymer, it has some structural water inside, and the kind of the structure depends on the size of the fiber.
Yeah, but I'm not analyzing how for example, it wouldn't matter here if I would analyze how the cellulose behaves dynamically here, but I'm just taking a piece of cellulose, a local piece, and see what happens over these methods. Right. For example, cellulose twists. And if I perform these simulations, I would see the twists, right? And it depends on the size, right? The twist, right? But if I analyze locally the small piece, the twist wouldn't matter, right? Because it's just in a small piece, there's just a little twisting angle. So it's very
Do you want to add something to that discussion, or?
No, I want to ask one question.
Okay. No. After you are the chief, you are the last one. In the last slide, I think it's the last slide when you computed free energy of solvation. That one. We start here with 0 and solvation
it's
free
so respect with the pure water. Actually, this is actually positive, right? Because but it decreases. So I'm just analyzing the effect, the net effect of the lignin around the cellulose. Actually, this is also
computation involves some kind of, because to compute solvation free energies, you would need in principle to do some kind of free energy perturbation to remove the solute from the solvent, something like that. In this case, there is only one computation
actually,
in
this
which
is not actually solvation free energy because this is with respect. This is delta solvation free energy.
Solvation free energy difference.
Yeah.
but is the because I was a little bit surprised because you are adding a solute that is that has a lot of hydrophobic parts, and you are adding this solute with a lot of hydrophobic parts into a progressively more hydrophobic solvent.
Yeah.
And I'm wondering if the hydrophilic effect is being correctly accounted.
Actually, you're touching a very delicate point because this theory, this approximation actually overestimates the hydration free energy, but it keeps the changes, right, in different situations. So the absolute value are usually higher than the experimental value, but the differences are usually well behaved, right? That's why the raw results would be like weird here. That's why.
I think I understand. I think Leandro has a point here. It's not a question of reason calculating, overestimating or not. The fact is, as you add more lignin, you have a solution that is becoming more and more hydrophobic. So to add another piece of lignin, it rather stay with their friends in solution rather than binding to hemicellulose. So at some point, as you increase the hydrophobicity of the solution, you would expect that the hemicellulose lignin free energy not to decrease. Is that?
Yeah, so I was even imagining in a simpler example. We are doing exactly with this solvent, but adding a spherical hydrophobic ball inside of this solvent. The solvation free energy would be very positive for pure water, and it would also decrease as you add a hydrophobic solvent. If you have a purely hydrophobic solute,
you mean instead of the lignin?
Yeah, instead of
you have
instead of the hemicellulose.
Okay.
If you have a purely hydrophobic solute, you probably get the same thing. That's expected.
Can I ask one last question?
Yeah.
I can ask anything. Could you comment, Rodrigo? Can you comment a little bit on the other problem? Just the fibrils in supercritical water or water in vapor or water under different conditions. That was the first part of the talk.
Here?
Yes. If I understand it correctly, after you heat it up, the binding between the two cellulose are stronger via the hydrophilic sections than via the hydrophobic sections.
But so we shouldn't compare this because the surface area are not the same. Because you can see here, this area is higher than this. Right? So
I was wondering about how
I
the
would
relation.
normalize the area and then compare this.
I was thinking of after pretreatment, the fibrils would aggregate more to expose hydrophobic surfaces. That's what the conclusion that I would get.
Yeah. That's true. But if you keep this format of the fibril, yes. But we can't say that this is intrinsic property of the surfaces. This is intrinsic property of the fibril, right? Because of this size of fibril. And yeah, that's true. Actually, this is also experimentally.
Yeah, so we'll do that.
Yeah, the hydrophobic surfaces are more exposed.
Any more questions? Okay, thank you. I think we have now